Sound is all around us, but some of our most common, everyday noises can reveal amazing secrets about physics. Welcome to our highly tuned and specialized test setup. An anechoic chamber designed to absorb all echoes. This means we'll only hear the direct sound of the impact and no reflections. Our level 2 sound meter captures decibel readings across the full frequency range of human hearing. Our shotgun mic captures clean audio signal. The sound camera pinpoints visually exactly where the sound originates. And the iPhone is used to record slow motion footage so we can see and hear the moment of impact in incredible detail. Sound is the result of oscillations that propagate in a medium, much like waves in a body of water. These waves create high and low density regions that are referred to as compression and rarefaction. The frequency, measured in cycles per second, or hertz, of these waves determine the pitch of the sound. The greater the frequency, the higher the pitch. We have broken down the frequency range of human hearing into 7 different frequency bands to better convey how that frequency band is perceived. You are now seeing the ambient noise level of our anechoic chamber overlaid on this graph. This ambient noise could be contributions from a myriad of sources, like the ground hum of electrical power, HVAC units, and many more. Let's explore the common sound of a coin dropping. In this slow motion footage, we can see the clarity of its movement. On the left-hand side, we see our sound cam footage. On top, notice the bright red spot. That shows the localized sound of impact. The bottom shows the spectra in real time. Now let's take a look at a static graph of the impact. Here we see a significant peak in our clunk region, a dip in the lower frequencies of our warm region, with a dramatic increase in all frequencies above this. This visual gives us insight into the complexities of the bright and rattling sounds of a coin drop. So quiet you could hear a pin drop. Well, let's take a look. Due to the unpredictable motion of the pin after striking the plate, let's take a look at a single impact. This spectra is devoid of that meaty clunk sound of the coin, and is mostly comprised of frequencies above 1,000 Hz that wisp, air, and hiss. This conveys that soft and angelic sound of a pin dropping. Let's now look at a water droplet striking a surface of water. Due to the sensitivity of the sound cam, we chose not to use it in this experiment for fear of getting it wet. Instead, let's take a look at the graph. Look at the increase in our boom region, a dip in the clunk region, and a rise in the warm region. Take note of the frequency drop-off during the wisp, air, and hiss region. This reflects a very mid-range and full of body sound. Let's take a look at all of the measurements on top of one another. See how much quieter the pin drop is compared to the rest of them. Notice how the water droplet is dominated by its mid-range frequencies. And see how the coin drop and the pin drop share a lot of characteristics in the higher end frequencies. It's incredible to think that these peaks and valleys are a visual representation of sounds we hear every day, We look forward to sharing more of our signal archive in the future. Thanks for joining us.